Okay, so let's get started. Let's do a quick recap of what we did in the last class. I think, yeah. Okay. So in the last class, we started looking at what is called convex functions. In particular, we looked at a specific case of convex. So we defined what a convex function is, right? So essentially, you take 2 points, look at the height. Let's say a function value at those 2 points, join the line. That line lies above the function, right? That's the definition of your convex function. So the consequence of that is, if you look at the Hessian, which is the second derivative, that's positive semi-definite, right? So it turns out that it's an if and only if condition. If the function is convex, then the Hessian will be positive semi-definite. If the Hessian is positive semi-definite, then the function is convex. We saw a few examples. Norm is convex, and then we looked at other examples also. Then we looked at another way of checking whether a function is convex or not. The first way is what? First principle, right? Go by definition. What is the second way? Second derivative, Hessian, prove that it's positive semi-definite. What is the third way? So you just pass a line through 2 points, x and y, which is x plus ty, and then look at that as a function of t. T is just one dimension, right? If you can prove that g of t is convex for all t, then the function f is also convex, right? So we saw that in the last class, and we used that to prove something. There is a small issue here. Can somebody, did you get a chance to look at this and figure out what the issue is with this? What is the issue? Any issue in this? The proof of this? No? Well, what did we assume? Well, x and y are positive, semi-definite, symmetric, all that is great. What is the other thing that we assumed? We assumed that this I plus x inverse y, right, has an eigenvalue decomposition, which is u sigma, u lambda, u Hermitian, right, which need not be true in general, right? So it works only if identity plus x whole inverse y is eigenvalue decomposable using unitary transformation, that is u lambda, u Hermitian, right? That was a gap, so which we will fix in today's class. And then we looked at a few more examples, and then finally we started looking at the unconstrained optimization problem, for which we proposed an algorithm called gradient descent, which was very easy. So you take a point, some initial point, look at the gradient direction, you move in the direction of the gradient, right? So that's what, you move in the direction of the gradient, right? So it's a simple algorithm. The way you update xv plus 1 is through this equation, right? So let me call this as GD. Okay? So whenever I say GD, this is the equation that I'm going to refer to, right? And then finally you do it for capital T rounds and return x capital T plus 1, right? That's what you return. We started analyzing this gradient descent algorithm, so which we will continue to do today as well. So first of all, we made a specific assumption here. The assumption is the Hessian is not only positive semi-definite, it's greater than or equal to some lambda times identity. So what do you mean by that? You look at the difference, right? The Hessian minus lambda times identity. That matrix is positive semi-definite. Okay, so if you assume that, this is called the strong convexity assumption. Okay, so this particular assumption is called strong convexity. I'll just write it here. So we say that the function is strongly convex if there is a lambda greater than 0 such that the Hessian is greater than or equal to lambda times identity. Then we say that the function is strongly convex. It's not only convex, it's strongly convex. So why is it called strongly convex? So if this is not true, what do you mean by, what is the condition? The condition is, of course, f is convex, right? That means Hessian should be positive semi-definite. That means for certain values of x, Hessian could be 0, right? You agree? Here 0 meaning, when you look at x transpose Hessian x, that will be 0. That means in some direction when you project, you'll get both will be orthogonal, right? So it will be 0, right? So when can that happen? That can happen when you have linear terms, right? For example, a bucket kind of a function, right? If you look at the bucket sort of function, the domain of the function where the function flattens, right? For those values of x, the Hessian will have, it will be greater than or equal to 0, right? So it won't be strictly greater than 0, right? So in which case it's convex, but it's not strictly, meaning it doesn't have a pointed shape like this, right? Do you agree? Because you take 2 points, if you join the two bottom line here, let's say if you have like this, if you join these two lines, these 2 points, then the function doesn't lie below it. It lies exactly, it overlaps, right? That's why it's called convex, but the other one is called strongly convex, when it lies strictly below. Okay, so now what is the consequence of this? So let's look at the gradient descent itself. Let's see what happens when you move one step from xt. So this is your xt and this is your xt plus 1. You have moved one step. I can write this as f of xt plus, how did you get this first equation here, this equation? How did you get this? Can somebody tell me what was the rationale behind writing this? What is this called? Remainder form of Taylor series, right? That's what we did. Then we said, well, if you look at the Hessian is greater than or equal to lambda times identity. So we could replace, I can think of xt plus 1 minus xt as x. So it's like x transpose Hessian x, right? Definitely that's greater than or equal to lambda times identity. So I just replace it by the same, right? We got lambda by 2 xt plus 1 minus xt transpose xt plus 1 minus xt. So it's like x transpose x, which is the inner product, which gives me the norm squared. So we got the norm squared, right? Then we invoke the GD step, right? So xt plus 1 minus xt is nothing but negative of the gradient, eta times gradient, right? So I just substituted gradient here. Gradient transpose gradient is again norm squared of the gradient. Remember, gradient is a vector, right? And you have lambda eta squared by 2, this. So essentially what we ended up getting was this equation here, right? So let me write this equation. So let's start. So what do we have? So proof of convergence. This is a very general proof. Okay, so even if you look at today's paper, right, let's say today's meaning, if you go to NeurIPS or ICML, whatever conferences, and look at the papers, the moment you see some of the proofs, you will recognize it's exactly similar to what we are trying to do. Okay, so there is a similar sequence of steps. So let's see, we got this, right? F of xt plus 1 is what? Is greater than or equal to f of xt minus eta times 1 minus, what do we have? Lambda eta by 2 norm of gradient of f xt whole squared, right? Do you agree with this? Okay, so now see, the function is like this, right? So this is your function and this point is the minima. Let me call this point as x star and the corresponding height as, I'll call this as p star, which is f of x star. This is the bottom, this is the minima. That's where we are heading towards, right? We want to get to x star. So now if you look at any xt, right, so xt will be somewhere here or here, anywhere, right? If you look at the corresponding value of the function, it's larger. Do you agree? So f of xt is definitely greater than p star. You agree? So if I replace f of xt by p star, I'll get a lower bound, right? Greater than or equal to minus eta times 1 minus lambda eta divided by 2 gradient of f of xt norm square. Okay, is that fine? Okay. So now what is it that we are saying? So let's look at this. F of xt plus 1 minus p star What is this difference? Okay, let me write this and say what is the difference. Is greater than or equal to minus eta times 1 minus lambda eta divided by 2 squared, right? You agree with this? So what is f of xt plus 1 minus p star? So let's look at it in terms of picture. Okay, suppose your xt plus 1 is here, right? This is where you are now. Now f of xt plus 1 is this, right? So this will be f of xt plus 1. What is p star? P star is basically at x star, right? This is your p star. So f of xt plus 1 minus p star is your gap, right? In fact, when you are doing, let's say, some machine learning task wherein you are figuring out what the neural network is, you will be doing some updates, right? Gradient updates. So that means each time you do gradient update, you are getting a new neural network, right? So after t plus 1 step, you will get a new neural network. Let me call that as xt plus 1, right? Now, if you look at the loss for that particular neural network minus the best loss, that's the gap, right? So this is the gap that we are looking at. We are saying the gap is greater than or equal to something, right? That's what we are trying to say here. Did I write everything properly? Let me just, okay. Okay, so now we have f of xt plus 1 minus p star is greater than or equal to minus eta times 1 minus lambda eta by 2, the gradient of this square. Okay, now I'll choose eta appropriately. How should I choose eta? What do you think is eta? How should I choose eta? It should be, basically this gives you a hint, right? If I choose eta as 1 by, let's say 1 by lambda, lambda cancels. 2, instead of 2 by lambda, I'll do 1 by lambda. So eta will be basically 1 by 2. So 1 minus 1 by 2 is 1 by 2. Eta is 1 by lambda. So it will be 1 by 2 lambda, right? So I can write such an inequality. Okay. Okay, so now I think I made a mistake here somewhere. Let me go back to the previous. So let's. Okay, so this is correct. xt plus 1 minus xt is minus eta. This is also correct. Okay, so just give me a second. I have to fix this. There is some issue. Okay, so let me tell you what is the issue. The issue is essentially I have to say if the gradient is small, then the gap is also small, right? This is very intuitive, right? So for example, is this, yeah, the other one. So if the gradient is small, which is true here, then this gap is also small. That's what I have to say, right? Let me probably rewrite this in a slightly different fashion. So let's say, I'll just rederive this. You take any point in the domain of the function. Okay. So now I can write this, right? F of I is greater than or equal to f of x plus y minus x transpose gradient of f of x then you have plus lambda by 2 x minus y norm square. This is clear, right? Strong convexity. Do you agree with this? You take any 2 points, strong convexity will give you this. Earlier we took xt plus 1 and xt, right? Now what we are going to do is we are going to substitute for y minus x, right? So what do we get here? This is greater than or equal to f of x. This is true for any xy, okay, in the domain. Plus, what is y minus x? Y minus x can be the gradient, right? So if you look at um, 1 second. Okay, so now let's okay, let's figure out what. So I want, so this is greater than or equal to the right hand side, right? So I'm free to choose this x and y. Now I'll choose y such that the right hand side is as close as possible to y, right? So how do I do that? I want to, sorry, I will ensure that it's as close as possible to the left hand side. How do I choose y? I have to choose y such that this is minimized, right? So choose y that minimizes this term. So how do you choose the y that minimizes this term? We will come back to this, okay? So we will come back to this. We'll fix this and come back. So how do you choose y that minimizes this? Right? So what y will you choose? It's like, okay, so maybe I'll write it here. It's like y minus x times the gradient of this thing plus some lambda by 2 x minus y whole square. So I want to minimize y. So how do you minimize y? By the way, this function is convex. It's like this whole function, and therefore how do I minimize with respect to y? So all that I have to take is derivative, right? So let's see, f dash of x plus 2 will cancel with this, x minus y with the negative sign, right? This is 0. So what is y? Y is lambda y, or I'll get x minus y will be equal to 1 over lambda f dash of x, or y is x minus 1 by lambda f dash of x. Do you agree? So essentially it says the y that you have to pick should be the gradient descent direction. This is the gradient update, right? xt plus 1 should be x minus this, right? Do you agree with this? Okay, now if you substitute this y in the previous equation here, so what do you get? You get, so you get f of y is greater than or equal to f of x. I'll keep this as it is. Y minus x is the gradient with the 1 over lambda, and if you simplify this, you will get 1 by 2 lambda norm of the gradient of f of x whole square. So this is exactly same as before, right? Now this okay. So what is it that we have done? So let's, I think this is little tricky. So we have chosen two x, let's say x and y. For this is true, right? But what I'm trying to do is I'm trying to make this as tighter as possible, right? For this fixed y, I'm going to make the right hand side as close as possible to f of y, right? So now if, how am I going to do that? I'm going to minimize the right hand side. That's what I did. By minimizing the right hand side, I got this, right? This thing. Do you agree? So this is true for any y, right? Do you agree? This is true for any y. Do you agree with this? take x and y, this is how it looks like, right? So since y is any point in the domain of f, choose y equal to let's say x star. Let's choose y equal to x star. So what will happen? This will be p star is greater than or equal to f of x minus 1 by 2 lambda norm of f of x, gradient of f x square, right? So now if I take it to the other side, or by rearranging, what do we have? We have f of x minus p star, this is the gap, right, is less than or equal to, right, 1 by 2 lambda the gradient of f of x square, right? So that means if your gradient is small, the gap is also small. Do you agree? You agree? So now all that I can say is if the gradient, right, so f of x whole squared is less than or equal to, I'll make this very small. How small? I'll make it some epsilon, right? So in fact I'll make it 2 lambda epsilon, right, less than or equal to 2 lambda epsilon implies f of x minus p star is less than or equal to epsilon. Do you agree with this? Is the flow clear? So all that I'm saying is a very intuitive statement. That is, if the gradient is small, then the gap is also small, which is very, very intuitive for convex functions, right? Strictly convex functions. So this is an important result. So how do I choose? If the gradient is less than 2 lambda epsilon, where did I get 2 lambda epsilon? Because if I substitute 2 lambda epsilon here, 2 lambda cancels and you get epsilon. So gap is less than or equal to, this is the gap, right? So what is this gap? This is the gap, right? So this is the gap, right? The gap is small provided the gradient is small. Is that fine, everyone? Any questions? Is there any questions? No? Fine. Okay. So I have to fix this now. So how did we, where did we go wrong? Okay. Maybe I'll let's revisit. Let's not do this. Let's keep this as is. Okay. F of xt. So this is greater than or equal to, let me call this whole constant as alpha. Okay, so it's alpha times the gradient squared, right? So let me call this as 1. So this is what we have, right? From 1, we have f of xt plus 1 minus f of xt is what? Is greater than or equal to alpha times the gradient of f of xt whole squared. Okay. If I sum both sides from t, overall t from 0 to capital T, what do I get? Okay, so summation t equal to 0 to capital T, f of xt plus 1, f of xt is greater than or equal to alpha times t equal to 0 to capital T, the gradient of, okay, fine. But this is greater than or equal to alpha times. So if you have, let's say, 3 numbers, a plus b plus c, that's always greater than or equal to 3 times the smallest, right? Do you agree? 1 plus 2 plus 3 is always greater than or equal to 3, because 3 times 1 is the least. So I'll do the following. So min over all t, gradient of f of xt whole square, right? Do you agree? with this? Okay. Now, what do we get on the left-hand side? What kind of a sum is this? An plus 1 minus an, summation over all n. What is that called? Your basic calculus. You would have studied these kind of things in your series, right? It's called telescopic series, telescopic sum. What is happening here? Let's look at this. For t equal to capital T, you have f of x capital T plus 1 minus f of xt. Plus, for t minus 1, you have capital f of xt minus f of xt minus 1, and so on. So this is basically, I'll write this here, f of xt plus 1 minus f of xt, that's the first term, plus f of xt minus f of xt minus 1, that's the second term, plus f of xt minus 1 minus f of xt minus 2, and so on. What is the last term? Last term will be t equal to 0, right? That will give me minus f of x 0. So what will happen? F of xt cancels, f of xt minus 1, f of xt minus 1 cancels. Everything cancels except the last and the first term, right? So this is f of xt plus 1 minus f of x0. So let's write that. F of xt plus 1 minus f of x0 is less than or equal to alpha times, well, this is t times the minimum over all t, the gradient of f of xt squared, right? Do you agree? Okay. Now, let's plug in alpha here. So what is alpha? Alpha is minus eta times 1 minus lambda eta by 2, right? Minus eta times 1 minus lambda eta by 2, capital T, minimum over all t, okay, square, right? Okay. So there is a minus here, right? So a is less than or equal to minus b, then b is greater than or equal to minus a, right? So that means the gradient alpha t times the gradient is greater than or equal to. So if I have negative, what will I get? Less than or equal to, right? So this implies eta 1 minus lambda eta by 2 times t, minimum over all t, the gradient of f of xt squared. Okay. Now right hand side is greater than or equal to left hand side. So if you have taken negative, it will be less than or equal to negative of the left hand side, right? So what is the negative? F of x naught minus f of xt plus 1. You agree? There was nothing wrong actually. It was fine. Good that I did something else, which also showed you the gap in terms of the gradient. Okay, so if I replace xt plus 1 by x star, what do you get? Suppose I replace this xt plus 1 by x star. Xt plus 1 will give you a function value which is larger, right? If I substitute x star, it gives me a function value which is smaller. So that means this is definitely greater than or equal to p star, because p star is the best, right? It's the bottom. You evaluate the function at any other point, it will give me a value larger, right? So now if I replace f of x capital T plus 1 by p star, it will always give me an upper bound, right? Further, right? I'm making the one that gets subtracted smaller, so it should be larger, right? So f of x naught minus p star. Okay, of course I'm assuming that the function is well behaved in the sense there is a minima. Okay, so it's not like going down forever. Okay, so now what do we get now? So we get this nice result. So we will make some adjustments here. Choose eta to be equal to what? I'll choose as before, right? 1 by 2 lambda or 1 by lambda. So if I choose 1 by lambda, what do I get? What do I get here? So minimum over all t, gradient norm squared at time t is less than or equal to f of x naught minus p star divided by eta is 1 by lambda, right? And this will be 1 by 2, right? It will be 1 by 2 lambda, right? So you'll have 1 by t times 1 by 2 lambda, right? Do you agree with this? Okay, now let me rewrite this. So this implies minimize over all t 0, 1, etc. t, gradient of f of xt is less than or equal to, let's go back, 2 lambda times f of x naught minus p star, this is the gap, divided by t, right? Do you agree? So what is it that I want? I want, if the gap has to be small, I want the gradient to be small. That's what we showed previously. Now, what is this saying? I want, so I want this right hand side to be small, right? I want the RHS to be small. What does that mean? If RHS is small, LHS is also small. What is LHS? The gradient. The gradient is also very small, right? So what do you mean by gradient being small? Remember, the gap is also small, right? That's what I want, right? So in fact, if you look at your gradient descent algorithm, maybe let me go back to the gradient descent algorithm. You run it t times, capital T times. How do you choose t? Eta we manage, right? We know what eta is because eta is 1 by lambda. We chose eta. That's fixed now. Now the question is, how do you choose capital T, right? You will write a for loop in your program for when you run gradient descent or stochastic gradient descent, but how do you choose that capital T, right? So this will tell us how to choose, right? I'll make this small. So what do you mean by that? This is what I'll do. Minus p star by t is less than or equal to epsilon, right? That means the minimum gradient is less than or equal to epsilon. That's when I stop. Okay. But the moment it is less than or equal to epsilon, what does it guarantee? The previous argument guarantees I'm very close to some delta close to the global optimum, right? It is guaranteed. Now, what does this imply? This implies t is greater than or equal to 2 lambda f of x naught minus p star by epsilon. That means if I run so many steps, I'm sure that the gradient at some point will be less than epsilon. That's where I can stop and you choose epsilon the way you want, right? How small epsilon should be, right? This results, so this proves convergence, right? Why? Can somebody tell me why it proves convergence? I should stop at some point. Well, I fixed capital T where I'll stop, but now what is this saying? This is saying if I say that I'll stop if, so think of it as a game. You say I will stop only if the gradient is smaller than 10 power minus 10. Well, for sure, if you run so many times, right, capital T greater than or equal to order of 1 by epsilon, right? Epsilon is 10 power minus 10. Then T should be of the order of 10 power 10. So maybe I'll write it like this. This is order of 1 by epsilon. Do you know what is order of? How many of you know what is order of? We go off. Okay, those who have studied algorithms, computer science people will know, right? Others? Fine. So this is what the order means, right? So we say that, for example, f of x is order of g of x. So what do you mean by that? If you take the ratio, for example, f of x over g of x, make the x go to infinity, the constant. That's called the order. Okay. E power x is of the order of e power 2x. Both are same. Order is same. Right. So what is this saying? So if you give me epsilon, right? If I run of the t, if I run the algorithm order of 1 by epsilon times, my gradient will be definitely greater than, less than or equal to epsilon. So I'll stop. Right. That's what it says. See, minimum, right? So I would know each point, I would know what is the gradient. So gradient should be at some point should be less than epsilon. So this guarantees that my algorithm will stop, right? Is that fine? Any questions? Those who are online, any questions? You got what I'm saying, right? So this is a nice result, right? So after so many steps, you'll have very small. So in fact, if you want, for example, this says if I choose my gradient square to be less than or equal to 2 lambda epsilon, gap is less than or equal to epsilon, right? So that means if you want the gap to be within epsilon, what should I do? I should ensure that the gradient is less than or equal to 2 lambda epsilon, right? So I can as well do it. Instead of this, what I'm going to do is I'm going to plug in 2 lambda here, 2 lambda epsilon. So what will happen? This will be 2 lambda epsilon. So this will be 2 lambda here, right? 2 lambda will cancel, and what do we get? F of x naught minus p star divided by epsilon. That will be the number of times you have to run to get epsilon close to the optimum, right? So in other words, what is this saying? If you run to get epsilon close to the optimum, have to run order of 1 minus epsilon. Well, to be very, very precise, I'll say f of x naught minus p star divided by epsilon times, right? So this completes the story. That means I'm epsilon close to the optimum if I run order of 1 by epsilon times. Very clear, right? So I think it's very difficult to remember what is f of x naught minus p star by epsilon. So I'll simplify. That's why order of notation is very useful. Can get epsilon close to optimum after order of 1 by epsilon rounds. If I run the algorithm order of 1 by epsilon times, I will be epsilon close to the optimum, right? Very easy to remember. Epsilon 1 by epsilon. Okay? You got the gist of the story, the big picture of what this result says. In fact, if you look at any algorithm, if you look at stochastic gradient descent, right, that's what is being used. Any papers, even papers, right, you see very, very similar steps. Strongly convex, and they just keep on doing that. Okay. Okay, so let me just. So I want to make a note of one thing. So there's a very, very interesting this inequality, right? So what is this inequality saying? I can rewrite it in a different fashion. Okay, so it says the square is greater than or equal to 2 lambda times the gap, right? This is what it's saying. It's some constant times the gap. The gradient squared at a point is greater than or equal to some constant times the gap. That's what it's essentially saying, right? I mean, gradient at any point. So there is a name for this. It's called PL inequality. In fact, this is one of the key tools in understanding deep neural networks. But PL stands for, I think, Polya, some, I don't know how to spell the second name. So what is so interesting about this, even if it is non-convex function, but if you can prove that it satisfies PL inequality, still there is some hope. You can go to global optimum, right? There is some hope under certain conditions. That's why it's very, very important. Anyway, this is just an aside. Okay, so any other questions? Any other questions? Okay. No questions? Okay, a small quick aside now. So because this is a data analysis course. So if I say gradient descent, then I should briefly talk about stochastic gradient descent also. We'll come back to this again, but I'll just say what is stochastic gradient descent. It's called SGD, right? In fact, when you say model.fit in your, let's say, TensorFlow, you pass this SGD as an argument, right? What it's saying is, in the background, I'm going to optimize my loss function with respect to neural network weights by following what is called gradient descent. In fact, what is called stochastic gradient descent. So what is stochastic here? Can somebody guess what is stochastic here? What is stochastic? All of you have taken introduction to probability, whatever equivalent course, right? Data analysis. All of you. Then what is stochastic? So it refers to randomness, right? So there is some stochasticity. It says stochastic gradient descent. That means gradient descent, there is some noise. So when can that happen? See, in this kind of algorithm, what you do is, when you implement gradient descent, there is another subroutine which will give me gradient, right? I'll query point X. The function will give me the gradient at that point, right? That's a subroutine or a function that you write. Those functions are always deterministic, right? Typically, for example, if you have X transpose QX, right? You look at the gradient of that, it will always give me QX. For a given X, it will always give me QX, right? It won't give me different values. That's called deterministic, no change. What is stochastic? Suppose I query, I ask you to find the gradient at a point X now, you'll give me something. If I ask a little later, you'll give me something else, right? It's noisy, it fluctuates. Why does it fluctuate? Okay, so just a quick background. Again, this is not the main topic. So remember this, so whenever we dealt with neural network, we wanted to minimize the loss function with respect to the neural network weights, and expectation is with respect to some data, right? So you are taking expectation with respect to data, right? This is a true average. Well, if I knew this true average, there is no scope for machine learning, right? You already know the answer pretty much. But what happens is you don't know the true expected value. For example, I give you a coin, right? If I know the bias of the coin, there is nothing, right? So you already know the bias. But what is interesting is, suppose you don't know the bias. Bias is probability of head. If you don't know the probability of head, what do? You toss it so many times, count the number of heads divided by the total number, right? That'll give me an estimate of the bias. Is that fine? So if I toss it more number of time, my accuracy of estimate is good, better, right? Even here, if you have a lot of data and I do the sample average of the loss function with respect to lot of data, I get the average which is close to true average, right? And then I have to, suppose I have, let's say, very huge data, big data, and then I compute the empirical average using that big data. That empirical average is always almost close to this average. Now I say you find the gradient. What is the problem? You have to find, so this is the proxy, right? So 1 over, let's say, n, I equal to 1 to n, sorry, capital N, loss of Zi, right? For each data point, you find the loss and compute the average. This is what you do. Instead of using this, you will use this because you don't know the true average. But if n is very large, and I ask you to find the gradient, what is the gradient? How do you find the gradient? 1 by n, I equal to 1 to n, gradient of this loss function with respect to w. Now you have to find the gradient with respect to w for each data point. If there are, let's say, 10 million data points, then you have to find 10 million gradients. Do you think it's easy? I mean, it's easy meaning conceptually easy, but if you want to, let's say you are training a very deep neural network, that means there are 10 million coefficients, a vector of 10 million, that's the number of coefficient neural network weights, that is your W. and you also have, let's say, 5 crore data points, then too complex, right? Nobody wants to do that. What do people do when you find? See, you have to do this each time you call the gradient. How many times you call the gradient? Even if it is convex, to get epsilon accuracy, you have to call 1 minus 1 by epsilon. If you want to have an accuracy of 10 power minus 5, you have to call it 10 power 5 times. It's ridiculous, right? So what do? Well, I say I don't want to use all the data and find the gradient. I'm okay with noisy gradients. So think of this as data, okay? So I have 1 to n. So what we do is we break this into smaller chunks, okay? Each chunk has lesser data, okay? Maybe 1,000 or 5,000, whatever. I'm going to, instead of using entire n, I'm going to use only 5,000 and compute the gradient. Each time I call a gradient, I'll pick this data, compute the gradient. Next time you call, you pick this data and so on. Randomly, you keep on picking some chunk and find the gradient with respect to that chunk of data, right? So this is called stochastic, because when you use this small chunk of data to compute your gradient, the gradient is not the true gradient. It will be a noisy version of the gradient. That's why it's called stochastic. What is the consequence? Gradient could be here, right? True gradient. But because it's noisy, it says you go here, right? You go in the wrong direction. That's what the challenge is, right? So if you do stochastic gradient descent, the challenge is that you may not go in the descent direction all the time, but on an average, you will go in the descent direction. That's the beauty of it, right? So you cannot be aggressive and take larger step. Eta cannot be like 1 by 2 lambda. You have to take smaller steps so that the noise gets averaged out, and overall you move in the direction of gradient descent, right? So is that fine? This is at least some big picture of what stochastic gradient descent is. Okay, any question? No questions? You guys don't have any questions? Understood everything? How many of you understood everything? Okay, how many of you did not understand everything? That means you should have some question, right? What is it that you didn't understand? Yes, one of you can tell. What is it that you did not understand? Don't hesitate. You can really ask. But you should not say, I didn't understand from day one. So then I may not be able to help you. But yeah, what is it that you didn't understand? Maybe you. Red color, right? Shirt. Yeah. Yes, you only. Yes. Not you, man. So this. Stochastic is like this. Suppose I toss the coin billion times. Count the number of heads divided by 1 billion. That gives me a very good estimate of the bias of the coin. It might say 0.362, which will be very close to the true, right? Do you agree? There is no randomness there. Almost randomness will disappear because of law of large numbers, right? It will average out. But if I allow you to toss it only 10 times, what will happen? You toss it 10 times, you will get 0.234. Again, you toss it 10 times and again compute the average, you will get 0.314. It will fluctuate around that 0.32, right? That's what stochasticity is all about. Even here, if you take large number of samples and compute the gradient of this gradient will be equal to the gradient of this, close to. But instead, you use a smaller chunk of data and find the gradient, what will you get? Like random coin toss 10 times, you will get a noisy estimate of your gradient, right? That's called stochastic because it's random, right? You won't get the true gradient direction. You'll get some noisy direction of the true gradient. Is that fine? Any other questions? Others? What about you? Understood? Okay, now let me repeat the same question. How many of you did not understand fully? Raise your hand. How can suddenly this one question made everything clear? No questions? Fine. Shall we move on? Okay. Okay, so okay, so let's revisit the previous problem, right? So I said there is an issue, right? So let's look at what is the issue here. So log det of identity plus ty, right? So Let's see what would be the issue here. Okay, so log of, this is the function, right? Log of determinant of identity plus x plus ty, right? So we want to show that this function as a function of t is convex, right? So now what we will do is, this y is, by the way, xy belongs to, right? This is something that we assumed. Symmetric positive semi-definite. Now, okay, let me take the example of y. So what is y? Y, because it's symmetric, I can write it like this, right? Do you agree? You agree with this? I can write it like this, right? What is lambda here? This lambda is like this, lambda 1, right? Diagonal with the diagonal matrix with the diagonal entries being eigenvalues. So now maybe I'll yeah, this I can write it like this, root lambda 1, root lambda 2, root lambda n, root lambda 1, root lambda n, 0, 0, u transpose. I can write this. When you multiply these two, what do we get? Same thing, right? Lambda. So let me call this matrix, let me define this matrix as lambda power half, okay? It's not square root of lambda, I mean, it's just a notation. Lambda power half is basically this matrix, okay? So now this becomes what? U lambda power half u transpose. But I can also write this as u lambda power half. I can write this as u transpose u lambda power half u transpose. Why is this true? Because u transpose u is identity. Now I will call this matrix, both are same, right? I will call this matrix as y power half. Okay, you understand the notation, right? Just take the eigenvalue decomposition, u lambda u transpose, take the square root of the diagonals, and you take u lambda power half u, that is u transpose, that is y power half. Okay, so basically I'm saying y is y power half times y power half. I can write this only for y belonging to Sn plus, okay, so not in general. So now what can you say about this y matrix? Y matrix, y power half matrix. What is y power half? It's u lambda power half u transpose. Do you think it's symmetric? Obviously, if you take the transpose of this, you'll again get u lambda power half u transpose, right? Lambda power half is square root of lambda 1, lambda 2, and so on, 0, 0, diagonal, right? It's positive semi-definite, obviously, right? So there is no problem. So this z power half also, or y power half also, belongs to. Do you agree with this? Okay. Now with this, let's do something. I think we need plus plus, because we are going to take the inverse. Okay. Okay. Now I'll do one thing. F of t is log det of identity plus x plus ty. I'll write it as y power half, y power half. I can write this, right? You agree with this? Okay. Now I'll pull y power half outside. So I'll pull y power half outside. So what do I get? I get, so I should have y power minus half here, identity plus x. I'll let's I might have to multiply t to x rather than t to y. Let's see that later. And then right multiplied by y power minus half. Y power minus half is the inverse of y power half. Okay, I'm just writing it as y power minus half plus t times identity. Of course, y power half is also here. Is that fine, everyone? Okay. So what is y power minus half? Let's go back. What is y power minus half? It's the inverse of y power half, right? It's u lambda power minus half u transpose. What is lambda power minus half? It's 1 by root lambda 1, 1 by root lambda 2, and so on, 1 by root lambda n. So when you multiply that by lambda power half, you'll get identity, right? See, I can do that because lambda is are non-zero. Okay, so if it is 0, it will get infinity and all that. That's why we need double plus here, right? All the eigenvalues are non-negative, strictly positive. Okay, so now what is the next step? I'll bring this here. Y power half times y power half is y. Log det of y times something is log det of y plus log det of something. So I have log det of y plus log det of what do we have here? So this thing is y power minus half identity plus x, y power minus half plus t times identity. This is a nice thing. Why? This is symmetric. Okay, I'll directly write this. This is belongs to s plus plus 1 because it's symmetric. I is symmetric, x is symmetric, I plus x is symmetric. So I'm multiplying by y power half and y power half on both sides, minus half on both sides, which are symmetric and positive definite. Therefore, the product is also positive semi-definite. Now I can do eigenvalue decomposition of that and then fill the gap. Okay, it's exactly same as what we did in the last class. Is that fine? Whatever we did in the last class is also correct, but it made a lot of assumptions there, right? We wanted the inverse times some matrix to be eigenvalue decomposable, but here we don't need. The proof works without that. Okay, yeah. Maybe you may have to write this, instead of writing t here, you might have to push t here. I don't know. So, but I don't think so. Not required. This is correct. Right. So now it's easy, right? So this will be v some sigma v transpose plus t times identity. Then again, I'll pull v out, sigma t times identity times v transpose, right? Then I'll push this here because of determinant. V transpose will be identity. I'll get sigma plus t I log det of this thing. And then what is log determinant of sigma plus t I? It's lambda 1 plus t, lambda 2 plus t, lambda 3 plus t, and so on, right? Product of all those. Log of the product is the sum. You will get log of some sigma I plus t, right? So which is concave. Done, right? So that's the proof. Okay, with this I'll stop. A small announcement. So tomorrow there is no class. I won't be there. Day after tomorrow there will be a tutorial which will be handled online. But these two classes I'll compensate it later. Day after tomorrow the TS will handle. So they will solve some problems which are relevant to the midsem. It will be online. Okay. Yeah. So we will compensate for these two classes later on. So one of the Mondays I'll take. I think 2 Mondays we'll take the class and finish. Okay. Thanks.